My name is Soren Meibom and I'm an astronomer at the Harvard-Smithsonian Center for Astrophysics. Over the past several years, you've heard how tremendously successful NASA's Kepler mission has been in helping us understand the diversity and the frequency of planets and planetary systems beyond our own. However, Kepler has also allowed us to make important discoveries about the stars these planets are orbiting. In this short video, I'll present to you our latest results from the Kepler cluster study.
The Kepler cluster study is a project designed to study stars and their planets inside these swarms of stars we call star clusters, and to do so with the data from the original Kepler mission, that is, the first 4 years of data from Kepler before its current mission called K2. One of our main goals with the Kepler cluster study was to make observations with Kepler to help us develop a method to determine precise ages for cool stars. That is, to build a clock for the stars. So what are cool stars, and why is it so important to know their ages well? A cool star is a star similar to our sun or smaller. They're very common in the solar neighborhood and indeed the most numerous throughout the galaxy. They also live long lives and therefore act as lampposts, lighting up even the oldest parts of our universe. So numerous and luminous, young and old, astronomers use cool stars to study the universe from its early days till recent times. And of course, in the context of Kepler and the search for planets beyond our solar system, cool stars are the kind of stars around which we have found the vast majority of such extrasolar planets. So why is it important to know their ages? Well, change happens with the passage of time. And just as organisms here on Earth change and evolve with time, so do stars and planets. And to understand this evolution, we must establish a sequence of events. For example, for us to understand the evolution of our own species over millions of years, we had to develop methods to date the fossil bones of our ancestors. In space, the formation and evolution of stars and planets, pairs of stars, clusters of stars, and galaxies takes place over hundreds of millions of years to many billions of years. And knowing the ages of the stars that make up these systems is as important to our understanding of astronomical phenomena as it has been to our understanding of human evolution to be able to date the bones of our ancestors. So now I have told you about the importance of cool stars and of knowing their ages. Now I will tell you that determining the age of a cool star is one of the most difficult tasks we astronomers are faced with. And the reason is this. As this drawing demonstrates, a cool star like our Sun looks almost the same for most of its life. That is to say, its size and mass, as well as its most easily observable properties, such as brightness and temperature, stay nearly constant throughout most of its lifetime. I usually drive this point home by asking you to imagine for a moment if the same was true for humans. Let's imagine that we were born as small babies, but by our first birthday, we looked like adults, and we stayed looking like that through our 20s, 40s, 60s, and even 80s, before we suddenly appeared old. If that was the case, we would not be able to look at another human being and tell his or her age. We would need to find something else about us that changed steadily and visibly as we grow older. And that is our challenge for cool stars, to find a property of a cool star that changes steadily with time and that we can observe. Luckily, there is one such property of a cool star. Its spin rate. Cool stars spin fast when they're young, and just like a top on a table, they spin slower and slower with time. Therefore, the spin of a cool star can be used as a clock that can tell us its age. And we refer to this method of using a star's spin as a clock as gyrochronology. The idea of this clock is simple. Here on the horizontal axis you have the stellar age in billions of years increasing to the right. On the vertical axis you have the stellar spin period in days increasing upward. So young, fast spinning stars will be found in the lower left part of this diagram, and slowly spinning old stars in the upper right. And we simply want to measure the spin periods for cool stars for which we already know the ages independently, and use these measurements to establish the relationship between spin and age for cool stars in general. Because if we can do that, we can then measure the spin period for any cool star in the sky and use the relationship to derive its age. So why do we need NASA's Kepler mission to carry out this seemingly simple task? Let me answer that by showing you how much of this clock we had built before Kepler and the Kepler cluster study. We had measurements of the spins and ages for the youngest cool stars, stars younger than about 600 million years. Now you're thinking, how can we know the ages of these young stars? And this is where the word cluster in the Kepler cluster study becomes relevant. Today, the only thing I want you to remember about star clusters is that we can determine their ages, and thus the ages of their stars, well, simply by plotting the colors and brightnesses for stars in clusters and examining the pattern we see. So the three rapidly spinning stars in the lower left part of this diagram represents measurements of spin rates of cool stars in young clusters. But beyond 600 million years, the only good information we had about their spin-age relationship was from our own cool star, the Sun, leaving us with a 4 billion year gap. And here is why. See, the way we determine the spin period of a star is by measuring the periodic changes in its brightness as dark spots on its surface move across its face, then disappears on the other side and comes back across the face again. Rapidly spinning young stars have many and big spots, and their brightness changes are therefore large and of short duration, and relatively easy to measure. This is demonstrated by the star and graph in the left panel. Older stars spin slower and have fewer and smaller spots, and their brightness changes are smaller and of longer duration, and thus much harder to measure. This is demonstrated by the stars and graphs in the middle and right panels. And so in star clusters with ages greater than about 600 million years, we have not been able to measure the spin periods for cool stars. And because of that, the construction of the cool star clock has been put on hold for decades, until Kepler was launched in 2009. Because with Kepler's highly precise measurement of stellar brightness over years, we've been able to break this deadlock. And so, in 2011, the Kepler cluster study produced its first measurements of spin periods for cool stars in the 1 billion year old cluster NGC 6811. And today, I announce that we have bridged the gap to the Sun by measuring spin periods for cool stars in the 2.5 billion year old cluster NGC 6819. These new observations, published in the journal Nature in January of 2015, allows us to trace the spin history of the Sun from its current 26-day period to a period of 18 days when it was 2.5 billion years old, and to 11 days when it was 1 billion years old, and so on. And they also put us in a better position for predicting how the Sun's spin rate will change as it grows older. But we are not restricted to stars just like our Sun, because our observations have established the spin-age relationship for stars that are both larger and more massive than the Sun, and stars that are smaller and less massive. And so, as you can see, we have made important progress in terms of measuring the spin history of cool stars. And in doing so, we have taken significant steps toward the construction of a clock that will be able to provide us with their ages, and with a precision better than previously possible.
Now let me end by emphasizing the value of this clock to our studies of planets and planetary systems beyond our own. The field of extrasolar planets is branching into investigations of the formation and evolution of planetary systems and of planets themselves and their atmospheres. Eventually, we hope to find true Earth analogs so we can gain some perspective of how normal or how unusual our own planet and planetary system is. And for all of these areas of study, knowing the ages of the planets and the planetary systems is essential.
Fortunately, a star and its planets form together and share the same age. So if we can determine the age of the star, we also have the ages of the planets orbiting that star. So as we find more and more rocky planets with sizes similar to the Earth and at distances from their host stars that may have given life a chance to evolve, the critical question becomes, how old are these planets? Because we know from studying our own planet how it went from being lifeless at 1 billion years, through primitive life at 3 billion years, to a planet teeming with complex, intelligent life at 4.6 billion years. And we may have to learn about the prospects for our own planet by studying other and older Earth-like planets orbiting other Sun-like stars. So clearly, age is highly relevant also to the question of life.
Thank you for watching, and thanks to my collaborators and to the funding agency supporting this work.